The human imagination has always reached beyond the sky, sketching worlds and wonders far stranger than our own. From the earliest myths to modern science fiction, people have filled the darkness above with gods, monsters, and impossible machines. Yet time and again, discoveries made by astronomers have revealed that the universe is not only stranger than our stories, but often far more bewildering. The cosmos has a way of humbling even our boldest ideas, showing us realities that could never have been guessed by intuition alone. For most of human history, the night sky seemed eternal and unchanging. Stars were thought to be fixed lights on a celestial sphere, tiny lamps scattered evenly in the heavens. The moon, the planets, and the sun drifted among them, moving like actors across a stage. But the backdrop itself felt immutable. When telescopes were first turned skyward in the 17th century, they shattered that illusion. Moons circled Jupiter. Saturn wore rings. The Milky Way was not a band of mist, but a vast congregation of countless stars. Even then, the first observers believed they were catching up to what imagination had already painted. But the more powerful our instruments became, the more reality outran fiction. Science fiction once imagined rockets that could take us to the moon in a single leap. In reality, spaceflight demanded engineering beyond anything dreamed in pulp novels. Yet those novels rarely described the landscapes we actually found. The moon was not covered in thick forests or ancient ruins, but in dust and basalt plains carved by impacts. Mars was not home to canals and cities, but to deserts colder than Antarctica. Still, disappointment at unmet fantasies gave way to awe at what actually existed. The truth was more alien than our myths. This contrast between expectation and reality has repeated across the centuries. Consider black holes. The idea of a star so dense that even light could not escape was proposed in the late 18th century by the English thinker John Michell. But even he considered it more a curiosity than a real possibility. For generations, the concept was dismissed as an absurdity, more suited to Gothic fiction than science. Yet modern physics not only revived the notion, but confirmed that these invisible giants truly exist, swallowing matter and bending space-time itself. Today, we even have an image, captured in 2019, of the dark silhouette of a supermassive black hole against the glowing gas of its host galaxy. What once seemed unthinkable turned out to be undeniable. The same applies to worlds beyond our solar system. For most of the 20th century, astronomers debated whether planets around other stars were common or rare. Science fiction confidently populated the galaxy with habitable worlds, but science had no evidence. That changed in 1995, when the first confirmed planet orbiting a sun-like star was announced. Since then, thousands more have been found, ranging from gas giants larger than Jupiter to rocky super-Earths, circling dim red dwarfs. Some orbit their stars so tightly that a year lasts only a few days, while others wander free, untethered to any Sunday. The true variety far exceeds what fiction dared to imagine. Our instincts, shaped by life on Earth, often fail us in the face of cosmic reality. Intuition suggests that stars should all burn in similar ways, that planets should resemble those in our own system, that galaxies should form neat spirals or clusters. But the universe repeatedly defies such patterns. There are stars that flicker with pulses sharper than the tick of an atomic clock, stars that harbor magnetic fields strong enough to erase hard drives from halfway across the solar system, and galaxies shaped like rings, chains, or ghosts. At every scale, from the smallest atom to the largest structures, reality forces us to reconsider what we thought possible. This is why astronomers sometimes say that the universe is not only stranger than we imagine, but stranger than we can imagine. It is not merely a place of vastness and emptiness, but of surprises lurking in every direction. Each discovery carries the thrill of contradiction, as though nature is deliberately mocking our assumptions. We expect one thing and find another, and each revelation leaves us both humbled and exhilarated. As we trace this journey through the strangest things ever found in space, we will see how often our expectations collapse in the face of evidence. The challenge is not only to accept these discoveries, but to recognize what they reveal about the limits of human thought. We evolved to survive in forests and savannas, not to comprehend the behavior of neutron stars or the expansion of space-time. And yet, through mathematics and observation, we can glimpse truths that stretch far beyond our senses. The story of astronomy is not just about mapping the heavens, but about expanding the boundaries of imagination itself. In the chapters ahead, we will encounter stars that should not exist, planets that defy logic, moons that conceal oceans, and galaxies made mostly of invisible matter. We will meet relics from the dawn of time and signals that hint at mysteries still unresolved. Each of these discoveries pushes us further into strangeness, reminding us that our place in the cosmos is far smaller and yet far more wondrous than we once believed. Let us begin this journey where all such stories must begin, with the stars themselves. For if the universe is stranger than we can imagine, the first proof lies in the existence of stars that by all rights should never have been born, and yet burn defiantly in the darkness. When we speak of imagination, it is tempting to believe that our minds can anticipate any possibility. Yet the universe often crafts realities that sidestep even the wildest speculation. In the 19th century, for example, no storyteller would have conceived of quasars, those remote beacons that blaze with the energy of entire galaxies. They were first seen as faint radio sources in the early 1960s, appearing to be no more than stars on photographic plates. When astronomers measured their light, however, they discovered something extraordinary. The spectral lines were shifted so far toward the red that it meant these objects were billions of light years away, shining with a luminosity greater than 1 trillion suns. What could generate such power? The answer was supermassive black holes devouring matter at the hearts of young galaxies. Until then, the very concept of a black hole was still controversial. Now it explains some of the brightest phenomena in the cosmos. No science fiction tale of the time had predicted such monsters. The lesson is repeated again with pulsars. In 1967, Jocelyn Bell Burnell and her colleagues detected an unusual signal in a radio telescope. It was a pulse of radio waves, repeating every 1.3 seconds with incredible regularity. At first, they considered, half-jokingly, that it might be a beacon from extraterrestrial intelligence, labeling it LGM for Little Green Men. But the explanation was stranger still. These pulses came from neutron stars, the collapsed cores of massive stars, spinning with unimaginable speed. Their beams of energy swept across space like the beam of a lighthouse, ticking with precision that rivaled human atomic clocks. The idea that a star could collapse into such a dense remnant was already a stretch for theorists, but that these remnants could rotate dozens or even hundreds of times per second was beyond prior expectation. Fiction might dream of alien signals, but nature provided something even more uncanny. Cosmic strangeness does not always arrive in violent bursts. Sometimes it reveals itself in subtle patterns that force us to reconsider our assumptions. For centuries, we believed the universe was static, eternal, and unchanging on the grandest scales. This view seemed reinforced by the stars, which to the naked eye maintained their positions from generation to generation. Yet in 1929, Edwin Hubble revealed that galaxies are not fixed, but are receding from us, and that the farther they are, the faster they flee. The universe itself was expanding. Later discoveries showed not only expansion, but acceleration, driven by some mysterious energy permeating space. Such a concept would have sounded like mysticism had it been suggested in earlier centuries. Instead, it is now a central pillar of cosmology. Our imagination could scarcely have prepared us for a universe that stretches faster and faster, propelled by an invisible force we still cannot name. When humans first looked upward, we imagined the heavens as perfect spheres, free of imperfection. Then telescopes revealed sunspots on our own star, blemishes that changed daily. We imagined the moon as a smooth orb, only to find it battered by craters from countless impacts. We imagined comets as omens or vapors, but science showed they are icy relics of the solar system's birth, wandering on long ellipses through deep space. In every case, reality has overturned appearances. Our intuition, forged in the ordinary scales of daily life, falters when confronted with celestial extremes. Rocks in our world crumble under their own weight if built too high, so we assume no mountain could rise infinitely. Yet Olympus Mons on Mars towers nearly 3 times the height of Everest, its bulk supported by a lower gravity and a crust that endured for billions of years. Human imagination might conjure giants, but only nature can construct them on such scale. The clash between expectation and reality is perhaps most striking when we confront the vast emptiness of space itself. To human senses, a vacuum is nothingness, a void where no air or matter remains. But the vacuum of space is not empty. Quantum physics tells us that even the void seethes with fluctuations, pairs of particles that appear and vanish in an instant. The very fabric of space and time is alive with activity. Dark energy, which drives the acceleration of cosmic expansion, may be tied to this restless sea of quantum fields. Thus, what seems like the simplest concept, nothingness, is in truth one of the most complex. Fiction has long imagined voids filled with creatures or phantom ships. Reality offers something subtler but more profound, a nothing that is never truly nothing at all. When we look at photographs from deep space, we are reminded how imagination is constantly being outrun. The Hubble Space Telescope, peering at what seemed an empty patch of sky, no bigger than a grain of sand held at arm's length, revealed thousands of galaxies. Each one contained billions of stars, and many of those stars may host their own planets. To gaze at that image is to feel the limits of imagination collapse. No story had ever conjured so vast a multitude. The universe does not simply exceed our dreams, it drowns them in magnitude. Our minds evolved to reckon with villages and forests, not superclusters of galaxies. Yet through instruments and mathematics we are able to perceive and even understand a fraction of this immensity. And so the paradox persists. We imagine boldly, we tell stories that push beyond the ordinary, yet each time reality unfolds, it leaves us gasping at how much further it has gone. Science fiction envisioned starships crossing between worlds, but did not imagine rogue planets drifting without stars. It envisioned crystalline worlds, but not entire planets potentially made of diamond. It envisioned alien oceans, but not the hidden seas of Europa or Enceladus, warmed by tidal forces instead of sunlight. Our creativity is vast, yet the cosmos is vaster. Each revelation is a reminder that we are apprentices to a universe whose imagination surpasses our own. This is why we study the sky, not only to map it, not only to navigate by its stars, but to learn humility. The cosmos continually demonstrates that human intuition is inadequate to the task. Only by questioning, measuring, and daring to believe the improbable do we draw closer to truth. We are not the first generation to be humbled in this way, and we will not be the last. Every telescope yet to be built, every mission launched, promises to reveal wonders stranger than fiction. The challenge is to keep our minds open wide enough to accept them. As this story unfolds, we will walk step by step through discoveries that once seemed impossible. We will see stars that glow with impossible ages, planets that travel without suns, moons that conceal alien seas, and galaxies composed almost entirely of invisible matter. Each of these findings contradicts intuition but stands firm on observation. They are the universe's way of telling us that our imaginations, bold though they may be, are still too narrow. To confront this truth is not defeat, but liberation. For if the universe is stranger than we can imagine, then every new discovery is an invitation to expand what imagination itself can be. The strangeness of the universe is not just in the objects we discover, but in the way they reveal themselves to us. Every new instrument seems to peel away another layer of mystery. And with each layer, we find something no one predicted. Before the 20th century, no one imagined that stars could die in explosions so powerful that they briefly outshine entire galaxies. Yet supernovae are not only real but crucial, forging the heavy elements that make up our world. Iron in our blood, calcium in our bones, gold in our jewelry, all were born in the fiery deaths of stars. In trying to imagine the heavens, no myth or story had prepared us for the reality that our very bodies are built from the ashes of long-dead suns. The imagination of humanity often leans toward the familiar, reshaping earthly things and projecting them onto the sky. We imagined alien cities that might resemble our own, alien beings with forms not so different from ours, alien worlds that followed climates similar to Earth. But when science probes further, it reveals differences so profound, they challenge our very language. Consider the gas giants, Jupiter, Saturn, Uranus, and Neptune are planets without solid ground. They are worlds where one could sink endlessly into clouds of hydrogen and helium, with pressures that crush and temperatures that soar. If we travel farther still, to exoplanets discovered in recent decades, we find gas giants that orbit so close to their stars that their atmospheres boil away, streaming into space like comet tails. These are hot Jupiters, planets so strange they defied classification at first. Their existence forced us to rewrite our theories of planet formation. Our imagination had pictured other systems as reflections of our own, with orderly orbits and familiar worlds. Reality presented something far wilder. Even time itself refuses to behave as we expect. Albert Einstein's theory of relativity, formulated in the early 20th century, revealed that time is not absolute, but elastic, stretching and bending, depending on gravity and motion. A clock carried near a massive object ticks more slowly than one far away. Light itself curves around stars and galaxies, creating mirages we call gravitational lenses. Fiction may have told stories of time travel, but reality showed us that time is already woven into the fabric of space, warped and twisted in ways that only mathematics can fully describe. The implications are not just intellectual puzzles. Without accounting for relativity, the satellites that provide us with global positioning would drift, their clocks losing sync with earthbound systems. The very maps on our phones work because the strangeness of space-time is real. The same applies to quantum physics, which governs the behavior of the smallest particles. Here, imagination was stretched further than ever before. Particles act like waves, appearing in multiple places until observed. They tunnel through barriers as if by magic. Two particles can remain entangled, linked across vast distances in a way that defies classical understanding. These are not science fiction tropes, but established facts, confirmed again and again in laboratories. They underpin technologies from semiconductors to lasers, yet they also remind us that the universe is not bound by the common sense we inherited from daily life. When science describes reality, it often sounds more fantastic than any invented tale. This continuous confrontation with the unexpected changes not only our knowledge, but our perspective. To accept that the universe is stranger than we imagine is also to accept that humility must guide us. We are a species that once thought Earth was the center of all things, that the stars were fixed lights, that the heavens revolved around us. One by one, those illusions were stripped away. Earth became one planet among many. The sun became one star among billions. The Milky Way itself became one galaxy among trillions. At each step, the universe grew larger, stranger, and more indifferent to human assumptions. And yet, rather than diminishing us, this revelation elevates our story. We are creatures capable of perceiving truths beyond instinct, of charting realities that even fiction could not predict. That is its own kind of wonder. As we stand now, gazing deeper into the cosmos than ever before, we are confronted by discoveries that outpace imagination almost yearly. Telescopes like the James Webb reveal galaxies forming in the first few 100 million years after the Big Bang, galaxies that should not be possible so soon. Signals like fast radio bursts crackle across the sky with unknown origins. Asteroids arrive from interstellar space, shaped like needles or fragments, hinting at processes far beyond our solar system. Each discovery adds to the catalogue of the impossible made real. Each whispers the same truth, that the cosmos is always one step ahead of us. But this should not discourage us. On the contrary, it means there will always be more to discover. The history of astronomy is a history of being surprised, of finding the unexpected and learning from it. What seems unbelievable today may be routine tomorrow. What feels like mystery may one day become knowledge, only to open new mysteries beyond. Imagination may lag behind reality, but it also grows from each encounter with the unknown. Science fiction writers of the next century will imagine far stranger things than we do now, inspired by discoveries we have only begun to glimpse. The universe, then, is not just a stage on which life unfolds. It is a constant teacher, challenging us to think beyond ourselves. It shows us that intuition is fragile, that certainty is fleeting, that the cosmos contains more than we can conceive, and it invites us to keep looking, to keep wondering, to keep expanding the boundaries of thought. For every answer we find, there are deeper questions waiting. Every time we think we have reached the edge of imagination, the universe reveals another horizon. And so our journey begins, not with the worlds or galaxies that lie at unimaginable distances, but with the stars themselves. For even among the stars, we encounter those that should not exist, and yet they shine. They remind us that in a universe stranger than imagination, the impossible is often real, and they will be our first step into the catalogue of wonders. Stars are born, they live, and they die. The details may vary depending on their mass, but the story is familiar. A cloud of gas collapses under gravity, ignites nuclear fusion, and shines for millions or billions of years. Eventually, fuel is exhausted, and the star ends either in a quiet fading or in a spectacular supernova. This rhythm of birth and death seems certain, written into the very laws of physics. And yet, the cosmos does not always follow its own rules. There are stars that refuse to die when they should, stars that appear older than the universe itself, and stars built from the strangest materials. They should not exist, but they do, blazing defiantly against expectation. Consider first the phenomenon of zombie stars. The very name sounds like something pulled from fiction, yet it describes a reality more unsettling than any story. When a massive star explodes in a supernova, it is supposed to destroy itself completely, leaving behind only a dense remnant, like a neutron star or black hole. But in recent decades, astronomers have found evidence of stars that survived their own explosions, battered and scarred, but still burning. These stellar zombies stagger on through the cosmos, defying the fate that should have claimed them. How can a star survive the destruction of its own core? The answer lies in the chaos of stellar death, where not every explosion unfolds as textbooks describe. Supernovae come in many forms, some triggered by collapsing cores, others by runaway nuclear fusion in white dwarfs. In certain cases, the blast may fail to fully unbind the star. A portion of the star may be cast off, while the core itself reignites and stabilizes, shining again, as if resurrected. Observations of peculiar supernova remnants have revealed surviving stars, displaced from their original homes and speeding away at hundreds of kilometers per second. These survivors carry chemical scars in their atmospheres, enriched with heavy elements forged in the explosion. They are cosmic phantoms, proof that even death is not absolute in the life cycle of stars. Zombie stars are not the only rebels against cosmic order. There is also the Methuselah star, officially catalogued as HD 140283. Located about 190 light-years away in the constellation of Libra, it is one of the oldest known stars in the Milky Way. Its chemical composition reveals it formed in the earliest days of the galaxy, with very little iron and other heavy elements. That in itself is unsurprising, since the first generations of stars were poor in metals. The puzzle arises when astronomers attempt to determine its age. By studying its brightness, temperature, and composition, researchers have repeatedly estimated that this star is about 14.5 billion years old. The problem is that the universe itself is only about 13.8 billion years old. How can a star be older than the cosmos that contains it? The Methuselah star embodies one of the strangest paradoxes in astronomy. The age estimates are uncertain, and refinements in stellar models suggest the star may be younger than early calculations implied, perhaps around 13 billion years. But even at that age, it presses against the limits of possibility. It means this star formed almost immediately after the Big Bang, in an era when galaxies were just assembling. Its existence tells us that the first stars and clusters arose quickly, seeding the universe with long-lived relics we can still see today. To gaze at the Methuselah star is to look across nearly the entire history of time, to a survivor that has endured almost since the beginning. Whether it is older than we think, or whether our models need revision, it is a reminder that cosmic clocks are not always easy to read. Other stars challenge our ideas not by their age but by their composition. Most stars, including our Sun, are made primarily of hydrogen and helium, with small amounts of heavier elements. But astronomers have discovered stars that are composed almost entirely of helium, carbon, or other unusual ingredients. These stellar oddities suggest histories of violent interaction. In binary systems, one star can strip material from another, peeling away its hydrogen envelope and leaving behind a helium core that still burns. In other cases, two white dwarfs may merge, producing stars with exotic chemical signatures. Some helium stars are so deficient in hydrogen that they cannot fuse in the usual way, yet they shine all the same, kept alive by processes that remain only partly understood. Then there are carbon stars, whose atmospheres are so rich in carbon that they glow with deep red light, their spectra marked by molecules of carbon compounds. These stars are not impossible in theory, but their abundance in certain regions challenges our understanding of stellar evolution. They dredge up carbon from their interiors in ways that standard models do not always predict. The skies of planets orbiting such stars, if they exist, would be cast in crimson hues, their chemistry alien to our own. Fiction has imagined strange suns, but nature provides stranger ones, built from the very ashes of stellar alchemy. The theme that unites these examples is simple. Stars do not always obey the rules we set for them. Our models, grounded in physics and observation, describe the typical cases, the majority paths of stellar life. But nature delights in exceptions. A star that survives its own death, a star that seems older than the universe, a star with a body built of helium or carbon alone. Each forces us to reconsider the boundaries of possibility. They are reminders that while physics is universal, the outcomes are as varied as the cosmos itself. These anomalies are not just curiosities, they are clues. Zombie stars reveal the complex physics of supernovae, showing that explosions can fail or falter in surprising ways. The Methuselah star tests our understanding of cosmic chronology, hinting that our models of stellar aging may need refinement. Helium and carbon stars teach us about mass transfer, mergers, and the unpredictable interplay between companions in binary systems. Each strange star is a laboratory, teaching us lessons about the forces that shape galaxies, and perhaps even the conditions for life. And yet, as strange as stars can be, they are only the beginning. Beyond them lies an even wilder menagerie of worlds, planets that drift without suns, planets made of diamond, planets coated in fire. The stars may defy expectations, but the planets turn imagination inside out. Before we explore those impossible worlds, let us linger a little longer among the impossible stars, for their stories are far from finished. When astronomers first began cataloguing stars with precision, they expected to find order, a family of stellar types that could be neatly arranged. The Hertzsprung-Russell diagram, created in the early 20th century, became a cornerstone of astrophysics. It showed how stars of different temperatures and brightness fell into distinct sequences, tracing their life cycles from birth to death. Yet even within this orderly framework, certain stars refused to fit. They occupied regions of the diagram where no star should logically exist. These misfits became puzzles, standing as evidence that stellar evolution was more diverse and chaotic than early models suggested. One class of such misfits is the hot subdwarfs. These are stars that burn with extreme heat, but with far less brightness than ordinary stars of similar temperature. They are thought to be remnants that have lost their outer hydrogen layers, exposing their hot helium cores. Some may have been stripped by companion stars. Others may have shed their layers in violent outbursts. What makes them remarkable is that they shine long after they should have faded. They are survivors of processes that ought to have extinguished them, hanging on in states that models had not predicted. Their very existence confirms that stars can take evolutionary detours that leave them wandering off the standard tracks. Equally baffling are stars like the blue stragglers found in ancient star clusters. Globular clusters are some of the oldest structures in the Milky Way, filled with stars nearly as old as the universe itself. Most of these stars are small and dim, having long since aged into quiet retirement. Yet within these clusters, astronomers find bright blue stars that appear much younger than their neighbors. How can such youthful stars exist in a population so ancient? The leading explanation is that blue stragglers are the products of stellar collisions or mergers, rejuvenated by fresh fuel. They are stars reborn through cosmic accidents, outliving the limits that should have bound them. To find them glowing within clusters is like finding a young sapling in the middle of an ancient forest, nourished by the fall of its neighbors. Among the strangest survivors are stars scarred by supernova blasts. When a massive star explodes, its companion, if present, may be hurled through space at incredible speeds. These so-called hypervelocity stars can race out of the galaxy altogether, traveling at more than 1,000 kilometers per second. Some carry chemical traces of the explosions that flung them outward, their atmospheres laced with elements forged in stellar death. They are stellar refugees, exiled from their birthplaces by catastrophes. Their existence tells us that even destruction can create new wanderers, stars that should not still be burning but that persist nonetheless, cast adrift across the cosmos. The Methuselah star remains one of the most provocative cases, but it is not alone in challenging cosmic chronology. Other ancient stars, low in metals and rich in hydrogen and helium, have been found throughout the halo of the Milky Way. These stars, known as population 2 stars, formed early in the galaxy's history and have endured ever since. Their survival is not impossible, but it raises questions about just how quickly the first generations of stars seeded the cosmos. If such ancient survivors are relatively common, it suggests that the processes of star formation began almost as soon as the universe cooled enough for atoms to form. In their light, we glimpse the faint echoes of the dawn of time. Even stranger are the so-called chemically peculiar stars, whose compositions defy expectation. Some are enriched with rare earth elements, others with lithium, which should normally be destroyed in stellar interiors. In certain cases, stars show lines in their spectra that suggest strong magnetic fields influence the distribution of elements in their atmospheres. These anomalies reveal the complexity of stellar chemistry, shaped not only by fusion in cores, but by magnetism, rotation, and interactions with companions. A star that shines with more lithium than expected is a direct challenge to models of how matter cycles through stellar lifetimes. Each chemical fingerprint is a clue, but also a reminder that stars are not as simple as fusion reactors. They are living laboratories, influenced by forces we are still striving to understand. The fascination with impossible stars is not purely academic. These anomalies inform us about the structure and history of the Milky Way itself. By studying the oldest stars, we reconstruct the conditions of the early universe. By examining survivors of supernovae, we learn how heavy elements are distributed and how galaxies evolve. By puzzling over strange chemistries, we uncover new insights into magnetic fields, stellar winds, and the processes that recycle matter into new generations of stars and planets. The stars that should not exist become guideposts, pointing us toward deeper truths about the cosmos. Yet there remains something profoundly unsettling about them. The idea that a star can be older than the universe challenges our most basic understanding of time. The idea that a star can survive its own death challenges our understanding of physics. The idea that stars can be composed almost entirely of exotic elements challenges our understanding of how matter behaves. Each discovery shakes the foundations of certainty, and in that shaking lies the true wonder. We are reminded that the cosmos is not obliged to fit our expectations, that the universe is under no obligation to be reasonable or comforting. It simply is, and our task is to follow where evidence leads. The strangeness of these stars also carries an emotional resonance. To gaze at the Methuselah star is to contemplate endurance beyond comprehension. To imagine a zombie star rekindled after catastrophe is to confront resilience written in fire. To see blue stragglers glowing among the ancient reminds us that even in old age, renewal is possible. The cosmos tells stories in its stars, stories not of perfection, but of survival, accident, and persistence. They are stories we recognize, for they mirror our own struggles against time and entropy. Perhaps that is why these impossible stars capture the imagination so deeply. They are not just anomalies, they are symbols. And so, as we trace the edges of what stars can be, we find ourselves always returning to wonder. Each outlier is a question mark written in starlight, beckoning us to look closer, to refine our theories, to accept that knowledge is provisional. The stars that should not be there are reminders that discovery is not about confirming what we expect, but about being surprised. They are cosmic teachers, forcing us to expand the limits of possibility. And just beyond them, waiting in the dark, are worlds, even stranger, planets that laugh at our categories and challenge our sense of what a planet can be. There is a paradox at the heart of astronomy. On one hand, stars are so numerous that their patterns seem predictable. Billions of them populate the Milky Way, and across those vast numbers we can find reliable rules. Stars of certain mass live certain lengths of time. Stars with certain compositions follow certain paths of evolution. The laws of physics do not change from one star to another. And yet, within this cosmic regularity, anomalies always emerge. It is as if the universe takes delight in reminding us that no model is complete, no chart of stellar life entirely accurate. Each time we believe we have solved the puzzle, another piece appears that does not fit. The Methuselah star embodies this paradox with particular force. If it is truly older than the universe, then either our age estimates for the star are wrong, or our measurements of the universe's age are incomplete. Cosmology tells us the age of the cosmos with remarkable precision, based on the cosmic microwave background and the expansion rate of galaxies. Yet here is a single star that appears to resist that conclusion. Even if newer calculations bring its age within the possible, it remains on the very edge of plausibility. It is like a witness whose testimony contradicts the rest of the evidence, not enough to overturn the verdict, but enough to keep us unsettled. One star can make us question the timeline of all things. Zombie stars do something similar by disrupting our sense of finality. We like to imagine stellar death as a definitive event, the curtain falling in a blaze of light. But in truth, death in the cosmos is messy. Some stars explode and vanish completely. Others leave behind remnants that shine again. Still others stagger on, half destroyed. The neat divisions of life and death, so familiar to us, blur when applied to the heavens. A star that should have perished, but instead reignites, is a challenge to the very metaphor of cosmic order. It tells us that even in the most violent processes, survival can emerge, improbable, but undeniable. Chemically peculiar stars extend the pattern, showing us that even the materials from which stars are made can defy expectation. Lithium that should have been destroyed is preserved. Rare earth elements appear in concentrations no model predicts. Magnetic fields shape atmospheres in ways that rewrite the rules of chemistry. To study such stars is to be reminded that physics is not a static code but a dynamic interplay. The rules exist, but the outcomes depend on conditions, accidents, and interactions too complex for us to foresee. The stars that should not be there are not violations of physics. They are expressions of physics in its most intricate and surprising forms. There is a deeper meaning in these anomalies. They tell us that the universe does not merely exist within the boundaries of probability. It also thrives on its extremes. For every billion ordinary stars, there will be a few that stretch the rules to their limits, and it is those few that teach us the most. By studying the exceptions, we sharpen our understanding of the rule. By contemplating the impossible, we expand the definition of what is possible. The universe is not only vast in number, but vast in variation, and it is in that variation that discovery flourishes. Emotionally, there is something haunting about these stars. To imagine a star older than the universe is to confront a riddle that brushes against the edge of reason. To envision a star surviving its own death is to see defiance written in fire. To picture blue stragglers glowing young among the ancient is to glimpse renewal where none should be. These images resonate because they echo human experience. We too seek endurance against time. We too survive catastrophes and emerge scarred but alive. We too find ways to begin again, even in the shadow of endings. In the stars, we find metaphors of resilience and paradox that speak to the deepest parts of our imagination. And so we must admit that the stars are stranger than the tidy diagrams we draw, stranger than the models we calculate, stranger even than the fictions we invent. They are messier, older, younger, more resilient, and more unpredictable. They do not belong to categories so much as they stretch them, reminding us that the universe is not designed to fit our minds. It is we who must expand our minds to fit the universe. In this sense, every impossible star is not a contradiction, but a challenge. It dares us to think bigger, to refine our science, to accept that mystery is not an error, but a signal that we have more to learn. The journey into stellar strangeness does not end here. If stars can astonish us with their resilience and their paradoxes, then planets can astonish us even more. For beyond the stars lie worlds that defy even the wildest categories. Some roam the galaxy without suns, alone in the dark. Some are made of diamond, glinting in alien brilliance. Some are oceans of lava, their surfaces seas of molten rock. Compared to them, even zombie stars seem tame. The stage is set, the curtain drawn back. We have seen stars that should not exist. Now we turn to planets that should not be possible. Were thought to be humble companions to stars, secondary actors, orbiting the true engines of the cosmos. Our own solar system seemed a model of order. Mercury, Venus, Earth, and Mars were small rocky spheres close to the Sunday. Beyond them, Jupiter, Saturn, Uranus, and Neptune were enormous giants cloaked in gas and ice. Each world circled obediently in a near-circular orbit, bound by gravity to the sun at the center. It was neat, symmetrical, and seemingly universal. Surely, astronomers thought, if other stars had planets, they would follow the same tidy pattern. But the discoveries of the last few decades have torn that assumption apart. The planets of the galaxy are stranger than we dared imagine. Some defy the very definition of what a planet island. Others wander the cosmos without suns, orphaned in the dark. Still others gleam with surfaces of diamond or boil with oceans of molten rock. They are rogue, impossible, and astonishing. The first confirmed planet around a sun-like star was discovered in 1995, orbiting the star 51 Pegasi. This planet was unlike anything in our solar system. It was a gas giant about half the mass of Jupiter, but it orbited its star once every 4 days, so close that its atmosphere was heated to thousands of degrees. Astronomers called it a hot Jupiter. Nothing in our theories had predicted such a world. According to the models, gas giants could only form far from their stars, where ice could condense and seed their growth. Yet here was a giant parked in an orbit closer than Mercury. The shock was profound. If the very first planet we found broke the rules, what other surprises awaited? The surprises came quickly. We found planets larger than Jupiter but denser than cork, puffed up like balloons. We found planets smaller than Neptune, but with thick, heavy atmospheres. We found super-Earths, rocky worlds bigger than our own but still far smaller than gas giants. A category of planet that does not even exist in our solar system. Each discovery forced us to widen our categories, to admit that our local family of planets was not the template of the cosmos, only one quirky arrangement among billions. Then came the rogue planets. These are worlds that do not orbit stars at all. Instead, they drift alone through the galaxy, cold and dark, with only the faint heat of their interiors. How do such wanderers come to be? Some may have formed around stars and been flung outward by gravitational encounters. Others may have formed directly in interstellar space from collapsing clouds, like failed stars. Observations suggest there may be as many rogue planets as there are stars, perhaps more. Imagine a galaxy where every star has its retinue of worlds, and in between, countless others roam unbound, each a lonely traveler in eternal night. To science fiction, planets were always tethered to suns. To reality, they are free to drift wherever chance has cast them. Rogue planets may seem inhospitable, but some might harbor internal heat from radioactive decay or tidal flexing. If they possess thick atmospheres or insulating blankets of ice, they could trap enough warmth to maintain subsurface oceans. Life, in principle, could exist even in the void. This possibility is unsettling and inspiring at once. It suggests that biology may not require sunlight at all, only chemistry and time. A rogue planet with an ocean beneath ice, drifting between the stars, could be a hidden cradle of life, invisible to us, except when chance reveals its silhouette. Not all strange planets are dark wanderers. Some gleam with exotic brilliance. One such example is the so-called Diamond Planet, officially catalogued as PSR J1719-1438b. It orbits a pulsar, the corpse of a massive star that exploded in a supernova. This planet is about 5 times the mass of Earth, but it is composed almost entirely of carbon and oxygen, compressed into crystalline form by immense pressure. In other words, it may be a giant diamond, larger than Earth itself. The idea stretches imagination. Worlds of jewel-like substance, glittering unseen in the void, are not dreams of alchemy but the outcomes of physics and chemistry on a scale beyond our own. Other impossible planets scorch with fire. Lava worlds orbit so close to their stars that their surfaces are seas of molten rock. One such planet, Kepler 10b, circles its star in less than 1 Earth day. Its surface temperature exceeds 2000 degrees Celsius, enough to keep rock liquid. Volcanic activity may be constant, the entire crust, a churning ocean of magma. If one could stand on its surface, the sky would glow with the blinding light of its star, while rivers of fire stretched to every horizon. These are not worlds for life, as we know it. They are worlds of pure elemental fury. Reminders that planets are not necessarily places to live but cosmic experiments in possibility. Then, there are planets with skies of glass and rain of metal. 1, HD 189733b, has winds that blow at more than 7,000 kilometers per hour, carrying vaporized silicate particles that condense into shards of glass. On this world, it literally rains glass sideways, a stormscape more violent than any fiction. Another planet, WASP 76b, is so hot that iron evaporates in its atmosphere, condensing as droplets of molten metal that fall as rain. These planets are laboratories of extremes, forging environments that stretch the concept of weather beyond recognition. Each discovery of a strange planet is more than a curiosity. It is a revelation about how systems form, evolve, and sometimes collapse. The hot Jupiters teach us that planets can migrate inward after formation, reshaping their orbits through gravitational interactions. The puffed-up giants show us how heat and stellar radiation inflate atmospheres. The rogue planets reveal the violence of early planetary systems, where gravitational battles can eject worlds into the void. The diamond planets and lava worlds remind us that chemistry and proximity create endless diversity. Each new category is not an exception, but an expansion of what we must consider possible. And yet, as strange as these planets are, they hint at something stranger still. For every bizarre world we have found, there may be countless others we have not yet glimpsed. Planets with oceans of ammonia, planets wrapped in permanent storms, planets orbiting dead stars, or trapped in eternal night. The galaxy is wide enough and old enough to contain them all. Fiction once imagined exotic worlds as backdrops for adventure. Reality has shown us that such worlds exist, and they are even wilder than we dared to dream. The discovery of strange worlds has also reshaped how we understand our own. Earth, for so long the standard by which planets were judged, now appears as just one member of a vast spectrum. In some ways it is ordinary, a rocky planet orbiting within a temperate zone around a stable star. In other ways it is unique, with liquid water on its surface and life flourishing across every corner. But when set against the catalogue of planets we now know, Earth is revealed as only one solution among many. The galaxy has shown us that planetary systems can be constructed in ways we never imagined, producing extremes that redefine the word possible. Among the most striking examples are planets locked in tidal embrace with their stars. On Earth, the Moon's gravity produces tides, but Earth itself still rotates freely. On many exoplanets, however, the gravitational pull of their stars has slowed their rotation until one side permanently faces the star, while the other side is locked in night. These tidally locked worlds are divided into halves of fire and ice. One hemisphere is scorched in perpetual daylight, the other frozen in eternal darkness. Between them may exist a twilight zone, a narrow strip where temperatures could be more moderate. Such a world is both hostile and fascinating, a natural experiment in climate pushed to its limits. Could life adapt to such a planet, clinging to the twilight between extremes? The question remains unanswered, but the possibility forces us to widen our vision of habitability. Other planets orbit not one star, but two. Binary systems are common in the galaxy, and some planets circle both suns at once, moving through gravitational dances far more complex than anything in our solar system. To stand on the surface of such a planet would be to watch two suns rise and set, their light mingling in alien hues. The climate of such a world would be shaped by the shifting brightness of its twin stars, sometimes gentle, sometimes harsh. Fiction once gave us the image of a desert world with two suns on the horizon, but reality has confirmed that such worlds exist. They are not only possible, they are common. Even more bizarre are planets that orbit dead stars. Around pulsars, those rapidly spinning remnants of exploded stars, planets have been found circling in tight orbits. These worlds endure in environments blasted by intense radiation, bathed in pulses of energy that sweep across space like cosmic lighthouses. How could such planets survive the explosions that created their pulsars? Some may be remnants of shattered companions, others may have formed from the debris left behind. In either case, their existence speaks of resilience in the face of cosmic violence. Where once there was destruction, now there are planets, proof that even death can give rise to new worlds. The diversity of planets also extends to their densities. We know of worlds so light that they are less dense than styrofoam, their atmospheres swollen by heat until they are vast and airy. Others are so dense that they must be composed largely of metal, iron spheres orbiting like cannonballs in the void. One such world, Kepler 10c, has been nicknamed a mega-Earth. It is more than 17 times the mass of our planet, yet it remains rocky, defying expectations that such a massive body would gather a thick atmosphere and become a gas giant. A world of iron and stone, 17 times heavier than Earth, is almost beyond comprehension. Mountains there would weigh down with crushing gravity. Oceans would be pressed into unimaginable depths, and yet it persists as a solid planet. It should not exist, but it does. We are also learning that planets come in families far stranger than our own solar system. Some stars have dozens of planets, arranged in compact orbits where they pass close to one another, each year measured in days instead of centuries. Others have systems tilted at extreme angles, planets orbiting perpendicular to the equators of their stars, as though flung into strange trajectories by past encounters. Some stars host hot Jupiters that scorch so close to their surfaces that they may one day be swallowed whole. Others harbor cold giants drifting at immense distances, barely tethered to their suns. The architectures are endless, a gallery of cosmic creativity. The question of habitability looms over all these discoveries. If Earth is not unique, then where else might life exist? Worlds, with oceans beneath ice, warmed by geothermal heat, may be common. Planets orbiting red dwarfs, the most abundant stars in the galaxy, may sustain atmospheres if they can withstand stellar flares. Even rogue planets, drifting in the dark, might harbor life in buried seas. Each new possibility stretches the definition of what it means for a planet to be alive. Life, if it exists elsewhere, may not need Earth-like conditions at all. It may thrive in places we once thought impossible. The search for such planets is still in its infancy. Our methods are limited, detecting dips in starlight as planets pass in front of their stars, or measuring the wobble of stars, tugged by planetary gravity. Yet even with these narrow tools, the diversity revealed has been staggering. If this is only the beginning, what lies ahead when new instruments peer deeper and with greater precision? Already the James Webb Telescope has begun analyzing the atmospheres of distant worlds, detecting molecules like water vapor and carbon dioxide. In the coming years, we may find signs of chemistry that hint at biology. And if the strangest planets are already real, who can say what stranger ones remain unseen? As we add each new world to our catalogue, the word impossible grows thinner. The universe delights in overturning our expectations. A planet of diamond, a planet of lava, a planet with glass storms, a planet locked between eternal night and endless day, all exist. They remind us that imagination, while vast, is not as vast as nature. Every time we think we have found the limits of planetary possibility, the cosmos extends those limits further. The most unsettling thought about these impossible planets is not simply that they exist, but that they may be far more common than we realize. For every strange world we have detected, there may be thousands more hidden beyond the reach of our instruments. Most planets do not cross directly in front of their stars from our point of view, so we cannot see their transits. Many orbit so far away that the wobbles they create in their stars are too small to measure. Rogue planets drifting without stars are nearly invisible, detectable only when they happen to pass in front of distant background light. What we have seen is only the smallest sample, a handful pulled from a cosmic ocean. If even this handful contains worlds of diamond, lava, glass, and metal rain, then the full ocean must contain wonders stranger still. Among the strangest discoveries so far are planets whose orbits seem almost absurd. Some circle their stars in only a few hours, hugging so close that they skirt the boundary between planet and star. Others travel on long, stretched paths that carry them hundreds of astronomical units from their suns, taking tens of thousands of years to complete a single orbit. A few even orbit backward, moving in the opposite direction to their star's rotation, as though flung into defiance by some past gravitational upheaval. These orbital oddities reveal the violent pasts of planetary systems, shaped by collisions, migrations, and near misses. They remind us that planetary systems are not clockwork mechanisms, but living, evolving arenas where chance and chaos hold sway. Another extraordinary kind of world is the ocean planet. Theory suggests that some planets may form with vast amounts of water, enough to cover their entire surfaces beneath global seas, hundreds of kilometers deep. Beneath such oceans, pressures would be so extreme that exotic forms of ice would exist, solid yet hotter than boiling water. Above, skies might be wrapped in dense layers of vapor, producing climates unlike anything we know. Such planets may be common around stars smaller than the Sun, where water can accumulate and remain stable. They are not simply Earths with more water, but entirely different environments, alien from the deepest trench to the highest cloud. The catalogue also includes planets that blur the line between planet and star. Brown dwarfs, sometimes called failed stars, are objects too massive to be planets, but too small to sustain hydrogen fusion like true stars. Some are dozens of times the mass of Jupiter, glowing faintly with leftover heat. They are worlds that almost became stars, teetering on the edge of stellar ignition. Do we call them planets, or do we call them stars? The boundary is not clear, and perhaps that is the lesson. Nature does not care for our definitions. It produces a spectrum, and our categories must adapt to what is real, not to what is tidy. There is also the haunting possibility of planets older than Earth by billions of years, perhaps even nearly as old as the universe itself. Around ancient stars in the halo of the Milky Way, planets have been detected that must have formed when heavy elements were scarce. What would such worlds be like? Composed largely of hydrogen and helium, perhaps with little rock or metal, they might be unlike anything familiar. And if life arose on such worlds, it would have had a head start of billions of years over Earth. The idea that civilizations might have risen and fallen on planets far older than ours is not fantasy but a sober possibility written in the ages of the galaxy. Each of these planets, whether rogue, fiery, crystalline, or oceanic, forces us to revise our understanding of what a planet island. Once, a planet meant a world like Earth, circling a star like the Sun, with familiar geology and familiar skies. Now it means something much broader, almost without boundary. A planet can be a frozen wanderer in interstellar space, a molten sphere of lava hugging its star, a diamond the size of Earth, or a gaseous balloon, too light to comprehend. The term planet no longer describes a narrow category but a universe of possibilities. The emotional power of these discoveries lies in what they reveal about our own place. Earth is not the model of worlds, but one peculiar instance. Its seas and continents, its mild climate and protective atmosphere, are the results of a particular set of accidents and balances. Elsewhere, those balances tipped differently, and the results are as strange as they are beautiful. To study impossible planets is to be reminded that we live on one of countless variations, not guaranteed, not typical, but simply one of many. That realization is both humbling and exhilarating. It tells us that life elsewhere, if it exists, will not be a mirror of ourselves, but something truly alien. The journey into the realm of impossible planets is only beginning. Each year brings new detections, new candidates, new surprises. The instruments we have now are powerful, but the instruments to come will be more powerful still. Telescopes on the ground and in space will soon reveal details of atmospheres, climates, and perhaps even surface conditions. They will show us not only what these planets are made of, but what they are like to stand upon. They will push the boundary between speculation and knowledge ever outward. If the past few decades have taught us anything, it is that the universe holds more planetary possibilities than we could ever have imagined. And if the future holds true, then the word impossible will continue to vanish from our vocabulary. We have now traveled from the strange stars that should not exist to the stranger worlds that rewrite our understanding of what planets can be. But planets are not the only companions of stars. Circling them too are moons, often overlooked, yet no less astonishing. Some moons conceal oceans beneath ice. Some spew geysers of water into space. Some are wrapped in atmospheres thicker than Earth's. If planets are stranger than we imagined, then moons are stranger still. And they are the next step. In our journey through the first turned telescopes toward Jupiter, they saw 4 points of light circling the giant planet. Galileo, in 1610, realized they were moons, companions in orbit. That discovery shattered the idea that Earth was the center of all motion and began a revolution. Centuries later, those same moons, along with Saturn's icy satellites, are teaching us another revolution, that life may hide in places we once thought impossible. Europa, the smallest of Jupiter's great moons, looks from space like a cracked marble, its icy shell scarred by lines and fractures. Beneath that frozen crust lies an ocean of liquid water, kept warm not by sunlight but by the tidal kneading of Jupiter's gravity. Though the surface is frozen, the ocean beneath may contain twice as much water as all of Earth's seas combined. This is no shallow pond but a global abyss, sealed in darkness yet stirred by energy from within. Where ice cracks open, water may rise and freeze, creating ridges and plains. Some regions appear chaotic, as though ice blocks have shifted like puzzle pieces, hinting at movement from the ocean below. To peer at Europa is to imagine a hidden sea, a world where life might evolve in darkness, warmed by heat from the interior and nourished by chemistry at the seafloor. Saturn's moon Enceladus is smaller still, barely 500 kilometers across, yet it has revealed one of the most astonishing secrets in the solar system. When the Cassini spacecraft flew past, it saw geysers erupting from the South Pole, plumes of water vapor and ice crystals shooting hundreds of kilometers into space. Instruments flew through the plumes and tasted salts, organic molecules, and evidence of hydrothermal reactions. Enceladus is not a frozen, dead rock. It is an active world with an ocean beneath its ice and vents that connect the sea to space. The geysers are invitations. They allow us to study the chemistry of an alien ocean without drilling through kilometers of ice. They tell us that Enceladus is warm enough for liquid water, chemically rich enough for complex molecules, and dynamic enough to exchange matter between surface and sea. If anywhere beyond Earth harbors life, this tiny moon may be it. Then there is Titan, Saturn's largest moon, bigger than the planet Mercury and more alien than any dream. Titan has a thick orange atmosphere, rich in nitrogen and methane. Its surface is sculpted not by water but by liquid methane and ethane, which rain from the sky, carve rivers, and collect in lakes and seas. Imagine standing on a shoreline beneath a dim sun, with waves lapping at a beach not of water but of hydrocarbons. The chemistry is exotic, yet it may echo the prebiotic conditions of early Earth, when life's molecules first assembled. Titan may not host life as we know it, but it provides a laboratory for what life could be under entirely different rules. And beneath its crust of ice, Titan may also hide a liquid water ocean, doubling the potential for habitability. Not all moons are gentle. Io, Jupiter's innermost large moon, is the most volcanic body in the solar system, its surface reshaped constantly by lava flows and sulfur plumes. Its fury is the result of gravitational torment, pulled between Jupiter and its neighboring moons. Ganymede, the largest moon in the solar system, has its own magnetic field and may harbor an ocean deep beneath ice. Callisto, ancient and battered, may as well. It seems the outer solar system is littered with hidden seas. Oceans are not rare exceptions. They may be the rule. The implications are staggering. For centuries, we looked for life on planets in the so-called habitable zone, where temperatures allow liquid water on the surface. But moons show another path. Heat can come not only from sunlight but from tides and chemistry. Life can exist in darkness, beneath ice, in oceans warmed from within. If Europa, Enceladus, or Titan hosts life, even microbes, it would mean that biology is not confined to Earth-like conditions. It would mean that the galaxy may be filled with habitats we once overlooked. Moons, circling giants, oceans beneath ice, chemistry thriving far from any star. The beauty of these moons is matched only by their mystery. Images of Europa's fractured crust, Enceladus's glittering plumes, Titan's hazy lakes stir not only scientific curiosity, but a sense of awe. They remind us that strangeness is not confined to distant exoplanets but lies within reach of our probes. And soon, we will go closer. The Europa Clipper mission is set to explore Europa in detail, searching for signs of habitability. Dragonfly, a rotorcraft, will fly across Titan's dunes and lakes, Future probes may dive through Enceladus's plumes with instruments designed to detect biology itself. The search for life beyond Earth may not begin with distant exoplanets, but with these moons. If we find even a hint of biology there, it will tell us that life arises wherever conditions permit, that it is not fragile or unique, but a natural consequence of chemistry and energy. That would be one of the most profound discoveries in history, reshaping science, philosophy, and culture. We would no longer ask whether we are alone, but what kinds of life the universe holds. Moons once seemed secondary, mere companions to planets. Now they stand as worlds of their own, with oceans, atmospheres, geology, and perhaps life. They are reminders that the universe is more inventive than we imagine, offering environments stranger and richer than any fiction. And as strange as they are, even they are not the strangest. Beyond these hidden oceans lie stars so dense they bend space, so magnetic they twist atoms, so precise they rival clocks. To leave the realm of moons is to enter the realm of stellar monsters. Among the countless weirdest that stud the night sky, stars appear steady, eternal, and familiar. They twinkle gently, rise and set with precision, and burn with a warmth that seems unchanging across human lifetimes. Yet, this calm is an illusion. Stars are not gentle fires, but nuclear furnaces, churning spheres of plasma held together by gravity and tearing themselves apart from within. And among them exist extremes so bizarre that they push the limits of physics. Objects whose properties defy not only common sense, but sometimes even our equations. These are the universe's weirdest stars, cosmic monsters that humble imagination. Perhaps the strangest of all are neutron stars. These are the remnants of massive stars that exploded in supernovae, their cores collapsing into objects no larger than a city, but with masses greater than the sunday. To grasp their density is almost impossible. A teaspoon of neutron star material would weigh billions of tons, more than every mountain on Earth combined. Their gravity is so intense that they warp space and time around them, bending light into curves and slowing the passage of clocks. To stand on their surface, if such a thing were possible, would mean being crushed instantly by gravity, stronger than anything else in the universe, outside of black holes. And yet, they exist, dozens of kilometers wide, spinning with speeds that blur comprehension. Many neutron stars reveal themselves as pulsars, lighthouses of the cosmos. As they spin, beams of radiation sweep across space. If one of those beams crosses Earth, we detect pulses with the regularity of a clock. Some pulsars spin hundreds of times per second, their precision rivaling or exceeding atomic clocks. For decades, their signals were so regular that the first astronomers to discover them wondered if they might be artificial. Jocelyn Bell Burnell's discovery in 1967 of a pulsing radio source was labeled LGM for Little Green Men, half in jest. The truth was even stranger. These were stars collapsed into remnants, so dense that quantum physics itself holds them up against gravity. Their ticking signals are the heartbeat of matter crushed beyond ordinary limits. Stranger still are magnetars, a rare subclass of neutron stars. While ordinary neutron stars already defy imagination, magnetars carry magnetic fields so strong that they warp atoms themselves. Earth's magnetic field is enough to guide compasses and protect us from the solar wind. A magnetar's field is 1 trillion times stronger, so intense that it could erase all credit cards on Earth from halfway to the moon. Within a magnetar's reach, chemistry itself breaks down, as atomic structures are stretched into strange shapes. These monsters occasionally release bursts of energy so powerful that they can be detected across the galaxy, outshining all other sources for a brief instant. To encounter such an object up close would be impossible. It would tear apart matter before it could even approach. The extremes of neutron stars and magnetars reveal just how far physics can be pushed. They are the limits of matter under pressure, where protons and electrons are crushed into neutrons, and where quantum mechanics and relativity collide. These stars are laboratories for theories we cannot replicate on Earth. They test our understanding of nuclear forces, of superfluid matter, of the behavior of particles under unimaginable densities. When astronomers study pulsars and magnetars, they are not only observing exotic stars, but probing the very foundations of physics. Not all weird stars are born from collapse. Some are giants that live strange lives before they die. Wolf-Rayet stars, for instance, are massive suns stripped of their outer layers, exposing cores that burn with ferocity. Their winds blow so strongly that they shed more mass in 1,000,000 years than the sun will lose in 10 billion. They blaze in brilliance, hotter and brighter than nearly any other star. These are cosmic titans nearing the ends of their lives, preparing for supernovae that will seed their surroundings with heavy elements. They are not steady suns but roaring infernos, short-lived and violent, their light often veiled by clouds of gas they themselves have expelled. To look at one is to witness a star burning itself to death. Then there are variable stars, whose brightness rises and falls in strange rhythms. Some pulse gently, expanding and contracting like cosmic lungs. Others erupt unpredictably, flaring with energy before dimming again. These variables challenge our sense of stars as steady beacons. Instead, they show that stars are dynamic, restless, and sometimes unstable. Their flickers tell us about the processes unfolding in their interiors, giving clues to fusion, convection, and the balance of forces that keep stars alive. Among them are Cepheid variables, whose regular pulsations became the yardstick for measuring distances to galaxies, turning strange behavior into one of astronomy's most important tools. At every scale, from pulsars to giants, the weirdest stars challenge intuition. We imagine stars as simple spheres of glowing gas, but the reality is stranger. Some are compact beyond imagination, others expand to sizes so vast they could engulf entire planetary systems. Some shine with steady brilliance, others with erratic pulses or terrifying bursts. Some live billions of years, others only a few million. Some are steady companions, others tear their neighbors apart. The diversity is endless, and each extreme teaches us something new about the physics of the universe. And yet, for all their strangeness, the weirdest stars are not rare exceptions. They are scattered across the galaxy, detectable with the right instruments, waiting for us to notice. They remind us that even the most ordinary-looking night sky hides marvels invisible to the naked eye. To the unaided gaze, a star may seem like any other, but hidden within its light may be the story of collapse, magnetism, or instability beyond comprehension. Each point of light is a question, and the answers are stranger than fiction. The strangeness of stars does not end with neutron stars, magnetars, and giants. Some stars play tricks with their companions, creating systems as violent as they are mesmerizing. In binary systems, where two stars orbit one another, the interaction of their gravities can strip material from one star to feed the other. This process creates accretion disks of glowing gas, sometimes producing flashes of light so bright they outshine the rest of the system. These are not quiet orbits but battles for survival, where one star slowly cannibalizes its partner. The result can be novae, sudden explosions as stolen hydrogen ignites on the surface of a white dwarf. In some cases, the feeding continues until the white dwarf exceeds its critical mass, collapsing into a neutron star or detonating as a supernova. To watch such a system is to see a cosmic predator devour its prey in slow motion. Even more spectacular are X-ray binaries, where a neutron star or black hole feeds on a companion. As matter spirals inward, it is heated to millions of degrees, emitting powerful X-rays detectable across space. These systems flicker and roar in bursts, evidence of matter crossing the threshold between star and remnant. They are gruesome but awe-inspiring, proving that the lives of stars are not isolated but intertwined. Death and survival are not individual stories but communal dramas, played out through gravitational entanglement. Some of the largest and strangest stars in the galaxy are red supergiants like Betelgeuse. These stars swell to sizes that defy belief. If placed in the center of our solar system, Betelgeuse would engulf the orbit of Jupiter. Its outer layers are so diffuse that they resemble a vast, tenuous cloud more than a solid sphere. Yet within, fusion continues, building heavy elements in shells that layer like an onion. Eventually, Betelgeuse will explode as a supernova, a detonation visible even in daylight from Earth. But even before that end, its variability and size make it one of the strangest objects we can observe. It is a reminder that stars do not remain steady, but evolve into forms so extreme they can barely be called stars at all. Beyond red supergiants are hypergiants, stars so massive and unstable that their lives are measured in only a few million years. They lose material in colossal winds, shaping nebulae that stretch for light years. They are rare, but their influence is immense, seeding their regions with heavy elements and shaping the birth of new generations of stars. One such hypergiant, Eta Carinae, erupted in the 19th century. In an outburst so bright, it became the second brightest star in the sky. The eruption did not destroy it, but it expelled several solar masses of material into space, forming a spectacular nebula. Eta Carinae remains unstable, a ticking clock that will one day end in a supernova or perhaps even a hypernova, one of the most powerful explosions known. Such stars remind us that cosmic violence is not confined to the distant past. It is unfolding even now, and Earth is close enough to witness it. Among the strangest of all stellar phenomena are pulsating white dwarfs. These are stars that should be in quiet retirement, remnants cooling slowly into darkness, yet some tremble and vibrate, their interiors ringing like bells. These oscillations allow astronomers to peer inside them, just as seismology on Earth allows us to probe our planet's core. The vibrations reveal details about the structure of degenerate matter, that strange state where electrons are packed as tightly as quantum physics allows. These faint stars, overlooked among brighter neighbors, become instruments for testing the laws of matter itself. They are reminders that strangeness can hide in the smallest and faintest objects, not only in the grand explosions of giants. Then there are stars that vanish before our eyes. In 2020, astronomers reported that a massive star in the galaxy, NGC 6946, had disappeared. No supernova was seen, no explosion detected. It seems simply to have collapsed into a black hole without a final blaze. If confirmed, such events would change our understanding of stellar death. We imagine stars ending with spectacular fireworks, but perhaps some slip silently into darkness. These disappearing stars are unsettling, as though the universe erases its actors without warning. They remind us that not all endings are visible, and that silence can be as mysterious as light. The variety of stellar oddities grows the deeper we look. Carbon stars, glowing red with the soot of their own fusion, enrich space with complex molecules. Blue stragglers, reborn through collisions, shine young in ancient clusters. Helium stars, stripped of hydrogen, reveal exotic compositions. Each is a reminder that stars are not simple furnaces, but laboratories of nuclear alchemy, producing elements and structures we can scarcely imagine. The weirdest stars are not exceptions, but the rule, proof that the universe thrives on diversity. For humans, these extremes evoke more than scientific curiosity. They inspire awe, tinged with fear. To know that neutron stars exist, dense enough to crush mountains into dust, is to glimpse power beyond anything earthly. To see Betelgeuse swell and flicker is to confront mortality on a cosmic scale. To watch stars cannibalize one another is to realize that violence is woven into the universe's fabric. Yet there is beauty in the violence, order in the chaos, and knowledge in the strangeness. The weirdest stars are not monsters in a hostile sky. They are teachers, showing us how matter behaves when pushed to its limits, how gravity sculpts energy, how time and space themselves bend under pressure. The cosmos does not run out of ways to astonish, and stars provide some of its most spectacular surprises. Consider the phenomenon of pulsars in binary systems, where the spin of the neutron star is accelerated by material falling from a companion. These are called millisecond pulsars, spinning hundreds of times per second, with the precision of cosmic clocks. The processes that drive them are violent gas pulled from a companion star spirals inward, transferring angular momentum and spinning the neutron star faster and faster. Yet the result is astonishing order. A star crushed to the size of a city, rotating faster than a blender blade, sends out pulses so regular that they can be used to measure the ripples of gravitational waves passing through space itself. These are stars that double as instruments, their strange nature turned into tools for probing the very structure of the universe. Beyond pulsars, there are stars caught in unusual states of balance, like Thorne-Jitkow objects. These rare entities are thought to form when a neutron star merges into the core of a red supergiant. Instead of destroying the giant, the neutron star settles inside, creating a bizarre hybrid. Outwardly, it looks like a swollen red star, but inside, unimaginable processes are taking place. The neutron star core acts as an engine, producing exotic elements through reactions not found in normal stars. Though few candidates have been observed, the very idea reveals how strange outcomes can arise from stellar collisions. Nature does not always destroy. Sometimes, it produces hybrids that stretch the imagination. Equally exotic are stars known as R Coronae Borealis variables. These stars fade unpredictably, dimming by factors of 1,000 before recovering months or years later. The cause is clouds of carbon soot condensing in their atmospheres, temporarily blocking their light. To an observer, they appear to vanish without warning, then reappear as though reborn. Such behavior shows that even seemingly quiet stars can cloak themselves in mystery. Their light carries the stories of chemistry and convection that play out within, giving us glimpses of the delicate balance between fusion, gravity, and the forces of stellar atmospheres. Another class of oddities are magnetically deformed stars. Some white dwarfs and neutron stars have such powerful magnetic fields that they are physically reshaped, squeezed along one axis and stretched along another. Their light can be polarized, split, and twisted by the field. These distortions turn stars into laboratories of quantum electrodynamics, letting us test theories about how light interacts with magnetism at extremes unreachable on Earth. They prove that stars are not only sources of light, but also canvases on which the laws of physics paint their boldest strokes. Even at the small end of the stellar scale, strangeness abounds. Brown dwarfs, hovering between planet and star, sometimes produce auroras brighter than Jupiter's. Some emit radio waves in bursts, hinting at processes we do not fully understand. Others are so cold that they could be mistaken for giant planets, with temperatures lower than a household oven. They occupy a twilight realm between definitions, neither fully star nor planet, yet abundant in the galaxy. Their very existence challenges the boundaries we try to draw. They remind us that categories are conveniences, not laws of nature. What ties all these anomalies together is the lesson they teach about expectation. Stars that should not exist, that should collapse or fade or behave predictably, instead surprise us. They push against the limits of our theories, exposing the cracks in our knowledge. Each new discovery forces a revision, a widening of our definitions. The universe seems intent on reminding us that it is not constrained by what is tidy, but guided by the deeper order of physics we do not yet fully grasp. To study the weirdest stars is to glimpse the horizon of ignorance, the frontier where science grows. There is also poetry in these extremes. A neutron star, invisible to the naked eye, spins in darkness, yet tells us of gravity and quantum pressure. A supergiant, blazing across light years, carries within it the seeds of future worlds, elements forged in fire that will one day become planets and life. A variable star fading into obscurity and brightening again mirrors the cycles of renewal and decay familiar to us all. Stars are not just physical entities, but symbols, mirrors of endurance, change, and transformation. Their weirdness makes them not alien, but strangely familiar. And yet, As strange as stars are, they are not the strangest structures in the cosmos. Beyond them lie galaxies that twist into impossible shapes. Galaxies so diffuse, they appear as ghosts. Galaxies composed almost entirely of invisible matter. If stars challenge our understanding of physics, galaxies challenge our understanding of structure itself. They are the next layer of cosmic strangeness. Vast systems whose mysteries extend beyond any single star. To pass from stars into galaxies is to move from the strangeness of matter to the strangeness of form, from the monsters of density to the puzzles of architecture. The journey continues, and each step only deepens the sense of the stars seem scattered at random, but beyond them lies a deeper order. Stars gather into galaxies, vast cities of light bound together by gravity. For much of history, galaxies were thought to be uniform, simple spirals and ellipses scattered across the cosmos. In the early 20th century, Edwin Hubble classified them into neat categories: spirals with their graceful arms, ellipticals with their smooth curves, irregulars that defied shape. It seemed the diversity of galaxies could be organized into a tidy diagram. Yet as telescopes grew stronger, the universe once again revealed that its imagination is wilder than ours. Galaxies exist that defy categories, structures so odd they look like cosmic jokes, so ghostly they barely seem real, so strange they force us to question what galaxies truly are. One of the most visually arresting oddities is Hoag's object, discovered in 1950 by Arthur Hoag. At first glance, it seems impossible. A nearly perfect ring of stars encircling a bright, spherical core. The ring is composed of hot blue stars, shining in youth, while the center holds older, yellowish stars. Between them is a dark gap, as though the galaxy were two separate systems bound in an impossible embrace. How such a structure forms is still debated. Perhaps a smaller galaxy passed through the core, triggering star formation in a ring. Perhaps it is the result of internal resonances shaping the stars into circles. Whatever the cause, the symmetry is uncanny, so exact that it seems designed. To see Hoag's object is to feel that the universe sometimes indulges in geometry, crafting perfection, not through art, but through physics. Even stranger are ultra-diffuse galaxies, faint shadows scattered across clusters. These galaxies can be as large as the Milky Way, but contain only a fraction of its stars, so spread out that they are barely visible. Some are so faint that astronomers did not recognize them as galaxies at all until recently. Their stars are like grains of dust scattered across immense volumes, giving them ghostly appearances. The question of how they formed remains a puzzle. Did they lose their gas before they could form stars? Were they torn apart by gravitational encounters with larger galaxies? Or do they represent a distinct path of galactic evolution? The strangeness is heightened by the fact that some ultra-diffuse galaxies seem to lack dark matter entirely, while others appear dominated by it. They are contradictions in starlight, teaching us that even the basic structure of galaxies is not fully understood. Other galaxies flaunt shapes that seem ripped from imagination. Some are collisional rings, formed when one galaxy punches through another, sending ripples of star formation outward in circles like waves across a pond. Others are warped spirals, twisted and bent by the gravity of neighbors, their arms flung into tidal streams, stretching across hundreds of thousands of light years. Still others merge into chaotic knots, where multiple galaxies blend into one, their stars mixed, their gas ignited in bursts of furious creation. To the human eye, these systems look like explosions frozen in time, sculptures of gravity written across the sky. They remind us that galaxies are not static pictures but evolving dramas, shaped by encounters and accidents on scales that dwarf imagination. There are also compact galaxies, the opposite of the diffuse kind, where stars are packed so tightly that they rival the cores of globular clusters. Some of these may be the remnants of larger galaxies stripped of their outer stars, leaving only dense nuclei behind. Others may be galaxies that formed differently from the start, condensing their material into intense cores. Whatever their origins, they defy the neat categories of spirals and ellipticals. They are galaxies compressed into jewels, shining with the brilliance of concentrated starlight. In every case, the oddest galaxies show us that the universe resists simplification. The tidy diagram of Hubble is only the beginning, a sketch of the most obvious forms. Beyond it lies a menagerie of structures sculpted by time, gravity, and chance. Some are beautiful, some are ghostly, some are incomprehensible, but all expand our sense of what galaxies can be. To gaze at them is to see the creativity of nature at its grandest scale. Whole systems of stars arranged in patterns that seem improbable, but are real. And just as with stars and planets, each odd galaxy carries clues. Their shapes and densities record histories of collisions, mergers, and dark matter. Their strangeness is not meaningless but instructive, telling us that even on the scale of hundreds of billions of stars, the universe delights in variety. As we uncover these oddities, we are forced to accept that our home galaxy, the Milky Way, is only one arrangement among countless possibilities. Its spiral arms and central bulge seem typical to us, but perhaps in the grand scheme, it is just one of many peculiarities. From rings to ghosts to collisions, the cosmos holds more forms of galaxies than our categories can contain, and in each form lies a question about what holds them together, what shapes them, and what role unseen forces play. For behind the strangeness of galaxies is a deeper mystery, one that hints at the invisible scaffolding of the cosmos itself. Galaxies, when viewed across cosmic time, reveal themselves not as static islands, but as restless structures, constantly reshaped by gravity and encounters. The strangest among them are often the results of collisions, processes that unfold over hundreds of millions of years, yet leave behind sculptures of breathtaking complexity. To watch two galaxies collide is not to see stars smashing directly into one another. Space is too vast for that, but to witness their gas and dust compressed into bursts of new star formation, their spiral arms twisted into elongated streams, their cores warped and fused. These interactions can produce tidal tails that extend for hundreds of thousands of light years, ribbons of stars arcing gracefully into the void. Some tails eventually collapse into smaller satellite galaxies, while others remain as scars across the night. In every case, collision is not destruction but transformation, a process that turns order into chaos and chaos into new forms of order. One striking example is the antennae galaxies, two spirals locked in the midst of collision. Their overlapping shapes and immense tidal tails resemble the open arms of an insect. In their centers, furious starbursts ignite, clusters of young stars forming by the tens of thousands. To look at the antennae is to see a moment in a process that will eventually blend the two into a single, larger galaxy. Our own Milky Way will undergo a similar fate when it merges with the Andromeda Galaxy in 4 billion years, producing a system likely to be elliptical in shape. The oddest galaxies, then, are not anomalies so much as snapshots of evolution, glimpses of transformations that every galaxy may one day endure. Yet not all strangeness comes from collision. Some galaxies show structures so unusual that they suggest influences we barely understand. Consider polar ring galaxies, where a central galaxy is surrounded by a ring of stars and gas, orbiting at right angles to its plane. It is as though two galaxies intersected in different dimensions, their components orbiting in perpendicular harmony. These systems challenge models of stability, yet they exist, their odd shapes stable for billions of years. The forces that create them may be mergers, accretions, or the capture of passing material. But whatever their origins, they demonstrate that galaxies can take on configurations far removed from Hubble's tidy diagram. Then there are the galaxies that appear empty at first glance, yet are held together by something unseen. Ultra-diffuse galaxies, in particular, raise profound questions. Some, like Dragonfly 44, appear to contain almost no stars at all, yet remain gravitationally bound, as though made entirely of dark matter. Others seem to lack dark matter altogether, their visible stars and gas moving without the extra mass we expect. These contradictory findings strike at the heart of cosmology. If some galaxies are ghosts of dark matter and others are almost purely starlight, then our understanding of how galaxies form may be incomplete. The oddest galaxies may be the keys that unlock the riddle of the invisible matter shaping the cosmos. Some galaxies are not even whole structures but remnants of past lives. Dwarf spheroidal galaxies, faint collections of stars, orbiting larger galaxies like satellites, may be survivors of tidal stripping. Their stars move slowly, their shapes diffuse, their dark matter content uncertain. They are fossils of ancient encounters, clues to the history of galactic cannibalism. Our own Milky Way has devoured several such dwarfs, their remnants scattered in streams across our halo. The Sagittarius dwarf galaxy, in the process of being torn apart by our gravity, leaves trails of stars that encircle us, like faint ribbons. These minor companions remind us that galactic evolution is not only about grand mergers, but also about countless small sacrifices, each contributing to the growth of giants. Beyond structure and form, the strangest galaxies also surprise with their behavior. Some host quasars, powered by supermassive black holes at their centers, emitting more light than entire galaxies, from regions smaller than our solar system. Others shoot jets of plasma stretching across millions of light years, fountains of energy propelled by spinning black holes. These active galaxies are as much engines as structures, transforming gravitational energy into radiant power. To see a galaxy glowing with a quasar is to glimpse a phase of furious activity, when the heart of the system outshines all its stars combined. Such behavior suggests that galaxies are not merely collections of stars but dynamic ecosystems, their cores influencing everything around them. In every direction we look, the universe defies our expectations of neatness. Galaxies form rings, tails, jets, and ghosts. They collide, merge, dissolve, and reassemble. They blaze with the power of black holes, or fade into diffuse shadows barely detectable. The diversity is staggering, and each case forces us to refine our understanding. The oddest galaxies are not curiosities but revelations, signposts, pointing to the forces that govern the cosmos. They remind us that structure arises not from simplicity but from complexity, from billions of years of interaction and transformation. They remind us, too, that our own galaxy is part of this vast process, shaped by past collisions and destined for future ones. To study them is to see our own fate written in distant light, and yet, for all their visible strangeness, galaxies also conceal mysteries in the unseen. Their motions, shapes, and structures hint at the presence of something invisible, a scaffolding that holds them together. That scaffolding is dark matter, the hidden mass that outweighs stars and gas, shaping galaxies from the shadows. Without it, galaxies would fly apart. With it, galaxies form webs stretching across the universe. To understand the oddest galaxies, we must turn to the invisible, to the forces that cannot be seen, but that define everything we observe. Galaxies are not only shapes of light, but records of invisible forces. When astronomers measure the rotation of spiral galaxies, they find that the stars at the edges orbit far faster than gravity, from visible matter alone, can explain. According to Newton's laws, the outer stars should slow down, pulled less strongly as distance grows. Instead, they whirl at speeds that suggest vast amounts of unseen mass are present, binding the galaxy together. This hidden component we call dark matter, and its presence is betrayed, not by light, but by motion. In a sense, the oddest galaxies are not the ones with strange shapes, but the ones that reveal most clearly the existence of something we cannot see. Their rotation curves are maps of an invisible skeleton holding them intact. Gravitational lensing offers another glimpse of this unseen framework. When a massive galaxy or cluster lies between us and a more distant object, its gravity bends the background light, distorting it into arcs and rings. Sometimes entire galaxies are stretched into luminous smears, magnified by the lens of another galaxy. These distortions allow astronomers to measure the distribution of dark matter within the lensing galaxy. What they find is that dark matter outweighs stars by factors of 5 or more, dominating the mass budget. The galaxies we see, with their shining stars and glowing gas, are only the frosting on a cake of invisible substance. The oddest galaxies are therefore not simply unusual in form, but profound in what they imply, that most of their matter cannot be seen at all. Some galaxies, however, seem to defy even this expectation. In recent years, astronomers have reported galaxies with little or no detectable dark matter, such as NGC 105-2-DF2. If true, these galaxies challenge the universality of dark matter, suggesting that some structures can form without it. How such galaxies exist remains an open question. Perhaps they were stripped of dark matter through tidal interactions, or perhaps our theories of gravity need refinement. In either case, they force us to confront the possibility that not all galaxies are bound by the same rules. They are anomalies that, like the Methuselah star or the rogue planets, refuse to fit within the standard framework. And it is often such anomalies that drive science forward. The oddest galaxies also remind us of the cosmic web, the vast network of filaments and nodes that stretch across the universe. Galaxies are not sprinkled randomly, but gathered along invisible scaffolding of dark matter. Clusters form at intersections, while voids expand between them. Immense regions, almost empty of galaxies at all. The shapes of galaxies and their groupings are products of this web. To look at a single galaxy is to see a bead on a thread, part of a pattern stretching billions of light years. The oddest galaxies may be those that reveal the web most clearly, tracing invisible threads through their positions and motions. They are not only structures in themselves, but markers of a deeper architecture, one that ties the universe together on the grandest scales. On a more human level, the oddest galaxies speak to the imagination. A ring galaxy like Hoag's object seems too perfect, as though a cosmic artist had drawn it with compasses. An ultra-diffuse galaxy appears like a phantom, a ghost drifting in the night. A colliding pair looks like a frozen explosion, energy and light, suspended in a moment that spans millions of years. These images stir awe not only because they are scientifically rich, but because they are aesthetically uncanny. They remind us that beauty is not limited to art or nature on Earth, but extends across the universe. The cosmos does not create with intention, yet it produces forms that echo design, symmetry, and elegance. Perhaps the deepest lesson of the oddest galaxies is that structure itself is stranger than we think. When Hubble created his classification, he thought he had captured the essential possibilities. Now we know that galaxies can be rings, lenses, ghosts, jets, and hybrids. They can be massive and bright, or faint and diffuse. They can hold vast amounts of dark matter, or almost none. They can blaze with quasars, or fade into near invisibility. They can be young, old, colliding, or dissolving. Each one is a chapter in a story too vast for any single diagram to contain. The universe, in its creativity, resists being boxed into categories. It is a lesson that repeats across scales, from stars to planets to galaxies. Reality is more inventive than theory, and behind all this strangeness lies a deeper puzzle. If galaxies are bound and shaped by dark matter, and if their expansion is driven apart by dark energy, then most of the universe is made not of the stars we see, but of invisible forces we do not yet understand. The oddest galaxies are therefore not only curiosities, but warnings, signposts pointing toward mysteries larger than themselves. They tell us that what we see is only a fraction of what is real, and that the true architecture of the cosmos lies hidden in the dark. To follow the trail of the strangest galaxies is to be led directly into the heart of the greatest cosmic riddle of all, the nature of dark matter. Looked at the night sky. The stars have appeared to tell us everything. They filled the darkness with light, and light seemed to be the story. Astronomy was the science of what could be seen, from the planets wandering among the constellations to the distant smudges that turned out to be galaxies. But in the last century, astronomy has revealed something far more unsettling. The visible universe is not the whole story. It is not even most of the story. The stars, galaxies, and glowing clouds we admire compose only a small fraction of reality. The rest, 95% of everything, is invisible. It is matter we cannot see and energy we cannot comprehend, shaping the cosmos while hiding from direct view. We call them dark matter and dark energy, names that are less explanations than admissions of ignorance. They are the greatest riddles of modern science, forces that shape galaxies, bend space, and drive the universe apart. The first hints of dark matter came not from theory but from stubborn evidence. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster, a collection of galaxies bound together by gravity. He measured their speeds and found them racing far faster than the visible mass of stars could account for. According to Newton's laws, the cluster should have flown apart. Yet, it remained bound. Zwicky proposed that some invisible matter, which he called Dunkel materie, must provide the missing mass. His claim was bold, and for decades it was treated as a curiosity. But more evidence followed. In the 1970s, Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies. The stars at their edges orbited just as quickly as those near the centers, defying the expected drop-off in speed. It was as if galaxies were embedded in vast halos of unseen matter, holding them together. Dark matter was no longer speculation. It was required. The idea is unsettling because dark matter is not simply dim stars, cold planets, or dust. Those are all visible in principle, reflecting or emitting light. Dark matter does not interact with light at all. It neither shines nor absorbs, neither glows nor casts shadows. Its presence can be inferred only through gravity, through the motions of galaxies, and the bending of light by gravitational lensing. Wherever astronomers look, they find that dark matter outweighs ordinary matter by about 5-1. Without it, galaxies could not hold themselves together, clusters could not remain bound, and the cosmic web could not have formed. The very structure of the universe depends on something invisible. What is dark matter? That is the great question. And so far, no one knows. One possibility is that it consists of particles beyond the standard model of physics, perhaps weakly interacting massive particles, or WIMPs. These hypothetical particles would have mass and exert gravity, but would interact so feebly with ordinary matter that they pass through stars and planets unnoticed. Another possibility is that dark matter is made of axions, ultralight particles predicted by certain extensions of quantum theory. Yet despite decades of experiments, detectors buried underground, observatories scanning for signals, no particle of dark matter has yet been caught. It is as though the universe has hidden the bulk of its contents behind a veil, daring us to guess. The mystery deepens with the realization that dark matter shapes not only galaxies but the largest structures in the cosmos. Simulations of the early universe show that dark matter clumped first, forming scaffolds on which gas could gather and ignite into stars. Without it, galaxies might never have formed at all. Even today, the cosmic web of filaments and clusters follows the distribution of dark matter, traced by gravitational lensing and galaxy surveys. We see the skeleton of the universe not by direct sight but by the way galaxies align along invisible threads. Dark matter is not decoration. It is the foundation. Ordinary matter is only the frosting on its vast invisible cake. If dark matter is the skeleton, then dark energy is the breath that drives the universe outward. Its discovery came in the 1990s, when astronomers studying distant supernovae expected to find that the expansion of the universe was slowing under gravity. Instead, they found the opposite. The expansion was accelerating. Galaxies were not just receding from each other, they were doing so faster, and faster. Something unseen was pushing space itself apart. That force we call dark energy, and it now appears to make up about 70% of the universe. Unlike dark matter, which pulls galaxies together with gravity, dark energy pushes them apart, acting as a repulsive pressure inherent to space itself. Some theories connect it to the cosmological constant, a term Einstein once introduced and then abandoned, representing energy intrinsic to the vacuum. Others propose quintessence, a dynamic field that changes over time. Whatever its nature, dark energy dominates the fate of the universe. If it continues as it is, galaxies will drift farther apart until distant stars vanish from view, leaving only local groups bound together. If it grows stronger, it could tear galaxies, stars, and even atoms apart in a scenario known as the Big Rip. The ultimate destiny of the cosmos depends on the nature of a force we do not yet understand. The coexistence of dark matter and dark energy is deeply paradoxical. One binds, the other disperses. One clumps into halos and webs, the other smooths and stretches space. Between them, they control the entire evolution of the universe, while the matter and light we know compose only a minor fraction. To study the cosmos today is to admit that we are in the shadows, observing with only 5% of the truth. The rest is dark, and yet there is progress. Surveys of the cosmic microwave background relic radiation from the birth of the universe show precise ripples that encode the density of dark matter and the influence of dark energy. Maps of galaxies reveal the clustering expected from dark matter halos. Observations of lensing confirm the presence of unseen mass bending light. Piece by piece, the evidence accumulates. We cannot see dark matter or dark energy, but their fingerprints are everywhere. They are as real as gravity, as undeniable as the stars, even if their identities remain hidden. There is a poetic irony in this. For millennia, astronomy was the science of light, of photons captured in the eye, and later on glass plates and detectors. Now it has become the science of the invisible, of forces that never touch light directly. The universe has humbled us again. What we thought was everything, the glowing stars, the radiant galaxies, is only a fraction. The true story lies in what we cannot see. The search for answers continues in underground laboratories shielded from cosmic rays, in particle accelerators probing high energies, in telescopes mapping the cosmos with increasing precision. Perhaps one day a particle of dark matter will strike a detector, or a subtle deviation in cosmic expansion will reveal the nature of dark energy. Until then, we live in a universe whose majority is mystery, and that mystery is not peripheral, but central, shaping everything we see. To contemplate dark matter and dark energy is to confront the limits of human knowledge. We live in a cosmos that is largely invisible, driven by forces we cannot yet name. And yet, there is wonder in this ignorance. It means the universe still has secrets, still offers frontiers for discovery. It means that science is not finished, but only beginning. Just as rogue planets and impossible stars expanded our vision of the possible, so too do dark matter and dark energy expand our vision of the real. The universe is stranger not only than we think, but than we can see. And still, even as we wrestle with the unseen, the cosmos whispers more mysteries through signals we barely comprehend. Bursts of radio waves arriving from billions of light years, stars dimming in ways we cannot explain, pulses once mistaken for alien beacons. The universe speaks in riddles, and each signal is a clue. Having seen the darkness that binds and drives the cosmos, we now turn to the ghosts and whispers that flicker across the sky, fleeting messages that hint at deeper, though not always in ways we expect. Sometimes it speaks in light, pouring photons across space for billions of years until they land in our telescopes. Sometimes it speaks in gravity, tugging stars and galaxies into patterns that reveal what is hidden. and sometimes it speaks in bursts and whispers, fleeting signals that defy explanation. Phenomena so strange that for a moment we wonder whether they are messages rather than accidents. These cosmic ghosts and signals remind us that the sky is alive with events we barely understand, transient flashes and dimmings that come and go, leaving behind riddles written in radio waves and starlight. One of the most haunting mysteries of recent decades is the phenomenon of fast radio bursts. First detected in 2007, these are millisecond-long pulses of radio energy that arrive from outside our galaxy. They are immensely powerful. In a fraction of a second, a fast radio burst releases as much energy as the sun emits in days. And yet they come from sources so small that they cannot be entire galaxies, only compact objects like neutron stars or black holes. The first bursts were detected only after the fact, buried in old data. But soon, more were found, each arriving from a different corner of the sky. They seemed to come from nowhere, flashing and fading before telescopes could turn to see them again. Theories multiplied. Perhaps they were collisions between neutron stars, releasing a final burst of energy before merging. Perhaps they were magnetars, flaring in magnetic convulsions. Perhaps, some dared to suggest, they were signals of intelligence, beacons flashing across the void. The mystery deepened when astronomers discovered repeating fast radio bursts, sources that pulsed not once but many times, though unpredictably. This meant they could not all be catastrophic, one-time events. Some had to come from objects that survived, capable of producing multiple bursts. One repeating burst, known as FRB 121102, was traced to a galaxy 3 billion light-years away, in a region of intense star formation. It flickered dozens of times, stubbornly refusing to explain itself. Eventually, some fast radio bursts were tied to magnetars within our own galaxy, linking them to violent magnetic outbursts. Yet, not all bursts fit this explanation. Some come from environments that do not match magnetars, others from distances that stretch plausibility. The puzzle remains unsolved, a ghostly reminder that the cosmos still sends signals we cannot interpret. Every new telescope, from the Canadian Hydrogen Intensity Mapping Experiment to the square-kilometre array now being built, promises more bursts, more clues, and perhaps eventually answers. But for now, each fast radio burst is like a knock on the door of the universe, sudden and unexplained. Not all cosmic ghosts come as bursts. Some come as dimmings, as stars that fade in ways too strange to ignore. The most famous is Kik 8462852, better known as Tabby's star. In 2015, astronomers and citizen scientists, examining data from the Kepler Space Telescope, noticed that this star flickered in bizarre patterns. Unlike the regular dips caused by orbiting planets, its brightness dropped irregularly, sometimes by 20%, sometimes by smaller amounts, sometimes lasting for days or weeks. No planet could cause such irregular and deep dimmings. Theories rushed forward. Swarms of comets, clouds of dust, or even, most provocatively, alien megastructures, vast arrays of panels, harvesting starlight. The idea of alien engineering captured imaginations, but the scientific process demanded restraint. Further studies showed that dust, likely from the star's own environment, was a more plausible cause, filtering light unevenly. Yet even dust does not fully explain the strange long-term fading of the star over a century of observations. Tabby's star remains enigmatic, a reminder that stars can behave in ways we do not yet understand. It is also a reminder of humility. When confronted with strangeness, humans are quick to leap to extraordinary explanations, but the cosmos is often stranger in natural ways than in imagined artificial ones. The history of astronomy holds another cautionary tale. In 1967, when Jocelyn Bell Burnell detected a regular pulsing radio signal, it was so precise that she and her colleagues labeled it LGM for Little Green Men, half in jest. The signal repeated with exact regularity, Unlike any known natural source, the truth turned out to be even stranger. Pulsars, neutron stars spinning rapidly, emitting beams of radiation like cosmic lighthouses. What was first suspected as a message from intelligence became one of the most profound natural discoveries of astrophysics. The universe did not need aliens to produce marvels. Its own physics was wondrous enough. Even so, the possibility of intelligence cannot be dismissed entirely. For decades, projects like SETI, the search for extraterrestrial intelligence, have scanned the skies for signals that cannot be explained by natural processes. So far, no confirmed detections have been made. A handful of candidates, like the famous WOW signal of 1977, remain tantalizing but unexplained, never to repeat. The silence may mean that we are alone, or that civilizations are rare, or that their methods of communication are beyond our recognition, but the very effort reveals something profound. We listen because we know the universe is capable of surprises, and because even a single verified signal would change everything. Signals also come in other forms. Gamma-ray bursts, discovered in the 1960s by satellites monitoring nuclear tests, turned out to be the most powerful explosions in the cosmos since the Big Bang. Some are caused by merging neutron stars, others by collapsing massive stars. They blaze with such intensity that they can outshine galaxies for brief moments. For years they were mysteries, ghosts flashing without warning. Now we understand some of their origins, but they still remind us how sudden and violent the universe can be. Even gravitational waves, ripples in space-time first detected in 2015, can be thought of as signals. They arrive not as light, but as distortions in distance itself, stretching and squeezing detectors on Earth by less than the width of a proton. Yet from those tiny ripples, we can hear the collisions of black holes and neutron stars billions of light years away. Gravitational waves are a new language, the universe speaking to us not in photons, but in vibrations of the fabric of reality. They were ghosts until recently, predicted but unseen. Now they are signals that add to our growing conversation with the cosmos. The strange thing about these cosmic ghosts and signals is not only their variety, but their fleeting nature. They appear without warning, last for moments, then vanish forever. To catch them requires vigilance, networks of telescopes, watching the sky continuously, data sifted by algorithms, and sometimes by human eyes. They remind us that the universe is not static but dynamic, full of transients that flicker and fade. They remind us that discovery often depends on being ready when the unexpected happens. What do these signals mean for us? On one level, they are puzzles to be solved, phenomena to be explained by physics. On another, they are metaphors for the act of listening itself. Humanity, small and brief, has built instruments capable of hearing the universe across billions of light years. We are tuning in to messages not meant for us, echoes of processes indifferent to life. And yet, in hearing them, we find connection. We find wonder in knowing that stars, black holes, and galaxies leave signatures we can detect. The ghosts become guides, leading us deeper into the unknown. As strange as these signals are, they are not the oldest or the faintest. Beyond them lie relics from the dawn of time itself, fossils of light and matter, preserved across cosmic ages. The universe does not only whisper in bursts and dimmings, it also carries echoes of its own birth, backgrounds that tell us what happened in the first seconds. To leave the domain of cosmic ghosts is to step into the archaeology of existence. Uncovering relics that date back to the origin of everything is not only filled with bursts and signals of the present, but also with fossils of the past. These relics are not stone artifacts or buried ruins, but patterns imprinted on space itself, messengers that have traveled across billions of years to tell us how the cosmos began. If cosmic ghosts and signals are fleeting voices, then these relics are ancient echoes, preserved in the fabric of reality since the dawn of time. They are the closest we can come to seeing the birth of the universe. the surviving remnants of an age long before galaxies, stars, or even atoms, as we know them. The most profound of these relics is the cosmic microwave background. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, it is the afterglow of the Big Bang. Light released when the universe was only 380,000 years old. Before that time, the cosmos was so hot and dense that matter and radiation were coupled in a plasma, scattering photons constantly. The universe was opaque, glowing like the surface of a star. But as it expanded and cooled, electrons and protons combined into neutral atoms, allowing light to travel freely for the first time. That light, stretched by the expansion of space, now fills the sky as microwave radiation, nearly uniform in every direction. It is a snapshot of the universe in its infancy, a fossil of its first breath. When first discovered, the cosmic microwave background seemed smooth, nearly featureless. But precise instruments, from the Cosmic Background Explorer to the Wilkinson Microwave Anisotropy Probe, and finally the Planck satellite, revealed faint ripples, tiny fluctuations in temperature and density. These ripples are the seeds of all structure. Where the density was slightly higher, gravity gathered matter to form galaxies and clusters. Where it was slightly lower, voids opened. To look at the microwave background is to see the blueprint of the cosmos, the pattern from which everything grew. It is as though the universe left behind a baby picture, showing us not only what it looked like, but how it would evolve. These patterns also encode information about the unseen. They reveal how much dark matter existed, how dark energy influences expansion, how space itself may be curved or flat. They even hint at the physics of inflation, the moment in the earliest fraction of a second when the universe is thought to have expanded faster than light, smoothing and flattening space. In this way, the microwave background is more than a relic. It is a Rosetta Stone, carrying the language of the early universe in faint variations of temperature across the sky. Yet the microwave background is not the only relic. The early universe also produced quasars, active galactic nuclei powered by supermassive black holes, appearing less than 1 billion years after the Big Bang. Their very existence is puzzling. Black holes, so massive billions of solar masses, should not have had time to form so early. Yet there they are, blazing as beacons from the edge of cosmic time. Some of the most distant quasars shine with a brilliance greater than 1,000 galaxies combined. Their light stretched into the infrared by expansion, but still detectable by our telescopes. They are fossils of the first giants, proof that the universe raced to build immense structures, far faster than theory expected. Each quasar is both a lighthouse and a riddle, telling us that the rules of growth in the early cosmos may have been different from what we imagine. The relics are not only in light but in matter itself. The very atoms we breathe, hydrogen and helium, were forged in the first minutes of the universe, in a process called Big Bang nucleosynthesis. In those moments, the cosmos was a nuclear furnace, hot enough to fuse protons and neutrons into the simplest elements. Hydrogen emerged in abundance, helium in smaller amounts, and trace amounts of lithium and beryllium. Everything heavier, carbon, oxygen, iron, gold, would come later, inside stars and supernovae. But the ratios of those primordial elements remain today, a chemical fossil of the universe's beginning. When astronomers measure helium in distant galaxies, they confirm the predictions of Big Bang nucleosynthesis, another relic testifying to our origins. Relics also arrive as visitors from beyond our solar system. In 2017, astronomers detected an object passing through the inner solar system that was not bound to the Sunday. Named Oumuamua, meaning scout in Hawaiian, it followed a hyperbolic trajectory, coming from interstellar space and returning to it. Its shape, elongated like a cigar or perhaps a flat disk, was unlike any asteroid or comet seen before. It showed no clear tail, yet it accelerated slightly, as though pushed by outgassing or something stranger. For months it was debated. Was Oumuamua a fragment of a shattered planet, an interstellar comet, or even an artifact of alien origin. No clear answer emerged, and the object soon slipped beyond reach. It remains one of the strangest visitors ever observed, a relic from another star system that crossed ours for only a brief encounter. Just 2 years later, another interstellar visitor appeared. This one, a comet named Borisov, after the amateur astronomer who discovered it. Unlike Oumuamua, Borisov behaved more like a traditional comet, with a visible tail and gas emission. But it, too, came from outside the solar system, a messenger carrying the chemistry of another star's nursery. Its detection confirmed that interstellar objects are not rare accidents but likely common, drifting between stars after being ejected from their home systems. Each one is a relic, a physical piece of another solar system, offering clues about how planets form elsewhere. The idea that interstellar objects can reach us expands the sense of connection. We are not isolated. Material flows between systems, carrying with it the history of other stars. Perhaps even life's ingredients could travel this way, seeding distant worlds in a cosmic exchange. If so, then relics like Oumuamua and Borisov are more than curiosities. They are threads in the fabric of panspermia, the possibility that life may spread across the galaxy through fragments of rock and ice. Relics also dwell closer to home, in the ancient craters and meteorites that strike Earth. Some meteorites contain grains older than the solar system, pre-solar grains, forged in the atmospheres of dying stars and carried here by chance. These tiny crystals are literally stardust, older than the sun, fossils of stars long dead. To hold such a grain is to touch a relic from before Earth existed, a fragment of time preserved in stone. All these relics, microwave background, quasars, nucleosynthesis, interstellar visitors, stardust tell the same story. The universe remembers. It remembers in light stretched across billions of years, in matter forged at the dawn, in objects wandering between stars. The past is not gone. It is embedded in the present, waiting for us to decipher it. The study of relics is more than archaeology. It is prophecy as well. By understanding how the universe began, we can glimpse how it will end. If dark energy continues to accelerate expansion, then the microwave background will fade, redshifted beyond detectability. If stars continue to burn, their ashes will fill space with heavier elements, relics of life's possibilities. If galaxies continue to collide, quasars will flare and fade, leaving only black holes. Each relic is a marker on a timeline that stretches from the first second to the far future. There is awe in realizing that we, fragile beings on a small planet, can detect and interpret these relics. We can read the faint glow of the microwave background, the spectrum of helium in distant galaxies, the trajectory of an interstellar visitor. We can reconstruct a history that spans 13.8 billion years. The relics do not speak in human language, but in photons, particles, and trajectories. Yet, we have learned to listen, and still, for all that we have learned, each relic raises new questions. Why did supermassive black holes form so early? What is the precise nature of the inflation that left its imprint on the microwave background? Are interstellar objects like Oumuamua common? And if so, what else might they carry? The relics whisper, but do not yet reveal everything. They promise more discoveries ahead, more strangeness still to come. As we gather these fossils of the cosmos, one truth becomes clear. Each strange find reshapes our understanding of reality. The universe is not a finished story, but a continuing revelation. With each relic we uncover, the horizon of the possible expands, and with every step into the unknown, we are reminded that the cosmos is not only older and larger than we thought, from the first telescopes that revealed the moons of Jupiter to the spacecraft that have flown past the edges of the solar system. Every step in astronomy has overturned assumptions. We expected other planets to be like Earth, and instead we found worlds of lava, ice, and methane. We imagined stars to be simple furnaces, and instead we found neutron stars, denser than atoms and magnetars, whose fields shred matter. We thought galaxies could be neatly classified, and instead we found rings, ghosts, and webs. We thought the universe was made of what we see, and instead we learned that most of it is invisible. Every strange discovery has widened the horizon of what we think possible. And still, the universe is not finished. Stranger discoveries lie ahead, waiting in the darkness, perhaps already hidden in the data we have yet to decode. The strangest lesson of all is that science fiction is often more cautious than reality. Writers imagined canals on Mars, only to be outdone by the discovery of subsurface oceans on Europa. They invented alien megastructures, only for astronomers to find stars like Tabby's star dimming in patterns so bizarre they seemed artificial. They speculated about faster-than-light travel, only for cosmology to reveal that the universe itself expanded faster than light in its first moments. Human imagination is bold, but the cosmos is bolder still. It is a reminder that the future of discovery is not bound by our current understanding. The laws of physics remain firm, but their consequences are often stranger than anything we predict. The next generation of instruments promises to open even more of the unknown. The James Webb Space Telescope has already begun peering into the first billion years, revealing galaxies so massive and bright they challenge our models of cosmic growth. The upcoming extremely large telescope in Chile, with a mirror 39 meters across, will probe exoplanet atmospheres directly, searching for signs of water, oxygen, or perhaps even biosignatures. The square-kilometer array will map fast radio bursts and pulsars across the sky, perhaps uncovering the engine behind their mystery. Gravitational wave observatories will listen for mergers of black holes and neutron stars across the cosmos, and perhaps even the faint hum of waves left over from the Big Bang itself. Each of these tools is a key, and the locks they will open are unimaginable. Exoplanet science in particular is poised for strangeness. Already we have found hot Jupiters skimming their stars, super-Earths larger than our own but smaller than Neptune, rogue planets drifting alone, diamond planets rich in carbon, and lava worlds glowing with molten surfaces. With better instruments, we will soon detect smaller, Earth-like planets and read the chemistry of their atmospheres. Will we find oxygen, methane, or other signs of life? Or will we find chemistries so alien that we struggle to interpret them? The likelihood is that the first habitable planets we find will not look like Earth at all, but will reveal forms of habitability we had not imagined. The universe may not give us a second Earth. It may give us stranger worlds altogether. The search for life extends to our own backyard. Missions are being prepared to fly through the geysers of Enceladus, to drill beneath the ice of Europa, to explore Titan's methane lakes with rotorcraft. These missions will not only look for chemistry but for biology itself. A single detection of life, even microbial, would be a revolution. It would prove that life is not a miracle confined to Earth but a natural outcome of planetary processes. It would tell us that biology is woven into the cosmos. And if life is found to be independent, formed from different chemistry or pathways, then the universe may be filled with endless variations of biology, each adapted to its environment. The strangest discovery may not be that we are alone, but that we are one among many. The mysteries of dark matter and dark energy will also continue to deepen. Perhaps new particles will be discovered, revealing the nature of the invisible mass that shapes galaxies. Perhaps new physics will be required, modifications to gravity that alter our fundamental understanding. Perhaps dark energy will change with time, hinting at an ultimate fate, stranger than the Big Rip or heat death. Whatever the answers, they will not leave our picture of the universe unchanged. They will redraw the boundaries of what we consider real. There may also be surprises we have not yet conceived. Just as pulsars were once mistaken for alien beacons, so too might the next great discovery come from data we do not recognize. Already artificial intelligence is helping to sift through mountains of observations, finding patterns no human eye could catch. Somewhere in that data may be phenomena we have no words for yet, signals that will force us to invent new categories. The future of astronomy may be less about confirming what we expect and more about being ready for what we cannot anticipate. For humanity, these discoveries are more than scientific. They reshape our philosophy and our sense of place. To know that the universe is filled with rogue planets and hidden oceans, with stars that collapse into neutron spheres, with galaxies held together by invisible matter, is to know that reality is more mysterious than myth. Each discovery humbles us, reminding us that our knowledge is provisional, our understanding incomplete, and yet each discovery also ennobles us, proving that fragile beings on a small planet can reach across time and space to uncover truths billions of years old. The final message of these strange findings is one of perspective. The universe is not tuned to human expectation. It is tuned to physics, to processes that operate across scales of time and energy beyond intuition. And yet, within that indifference, we find beauty. We find that stars explode, not only to die, but to create elements that form planets and life. We find that galaxies collide not only to destroy, but to seed new generations of stars. We find that even the invisible dark matter and dark energy shapes a universe capable of wonder. So what lies ahead? Stranger things, always. Worlds we cannot imagine. Stars we have not classified. Signals we have not yet heard. Each new discovery will widen the horizon of the possible, pushing back the frontier of ignorance. The universe is not finished surprising us. It is stranger than we think, and perhaps stranger than we can think. And yet, by listening, watching, and exploring, we draw closer to its truth. The night sky above us is not silent. It is alive with echoes of the past and hints of the future. To look up is to be part of a story that began long before Earth and will continue long after. Each discovery, each relic, each signal is a reminder that the universe is not only vast, but intimate, inviting us to wonder. Stranger still lies ahead, and in that strangeness is the promise of endless discovery.